In question 11, we have to find the drift velocity of the electrons in the wire, and the radius of the copper wire is 0.40 millimeter. Current is 5.1 ampere, and charge carrier density is 8.5 into 10 to the power 28. So you simply have to use the formula that is I is equals to NaQV, where A is the cross-sectional area of the copper wire, that is pi r square, as the cross-sectional area of a wire is that of a circle. N is the charge carrier density, which means the number of electrons or charge carriers per unit volume. Q is the electronic charge, that stands for 1.6 into 10 to the power minus 19. Current is given, that is 5.1 ampere, and V is the drift velocity. So simply we have to subject V from here, and we will get I divided by NaU. So the cross-sectional area of copper wire stands for pi into 0.40 into 10 to the power minus 3, converting millimeter to meter square. And you're getting 5.0 into 10 to the power minus 7 meter square. So if you put everything over here, you will get 5.1. N stands for 8.5 into 10 to the power 28 into area is 5.0 into 10 to the power minus 7. And electronic charge is 1.6 into 10 to the power minus 17. You simply will get the answer, that is 7.5 into 10 to the power minus 4 Newton per second. Question 12 is about the superposition of waves in a ripple tank. And we can see there are two sources, S1 and S2. Both sources are producing waves. And when these two waves interfere with each other, they will undergo constructive superposition and destructive superposition. Hence, at points where they will meet crest and crest, or trough and trough, or simply where they will meet in phase, the waves will undergo constructive superposition. And where they will be meeting out of phase, the waves will undergo destructive superposition. So the question is telling you what will happen in position A and position B. So we can simply see at point A, it aligns with the point of crest and crest meeting. As you can see over here, if you draw this line, you can see it aligns with the point of crest and crest meeting. So you can say point A will undergo constructive superposition, and hence point B will undergo destructive superposition. In questions like this, you simply have to write why it is undergoing constructive superposition and why it is undergoing destructive superposition. So let's write it down. Point A, it is undergoing constructive superposition. It is undergoing constructive superposition. And why is that? As waves, as waves are interfering in phase and have a path difference and have a path difference or whole number multiple of lambda. That is specifically n lambda, where n is equals to 1, 2, 3, and so on. So for B, it will happen destructive superposition, hence it is undergoing destructive superposition. It is undergoing destructive superposition as waves are meeting or interfering out of phase out of phase or in anti-phase and have a path difference and have a path difference of odd number multiple of half lambda, odd number multiple of half lambda, that is n plus 1 by 2. So when the waves are undergoing constructive superposition, the amplitude of the waves increases, and the waves are when they're undergoing destructive superposition, the amplitude of the waves decreases. In question 13, we can see there's a series circuit, and we have a fixed resistor of 5 kilo ohms and an LDR. We have to recall what is the meaning of an LDR. LDR is a light-dependent resistor whose resistance changes with light intensity falling on it. So if greater the light intensity falls on it, the lower is its resistance, which means resistance is inversely proportional to intensity of light falling on it. Okay. Now in this question, they're telling us to find the resistance of the LDR. You simply have to find the resistance of the LDR, and the question has given us the EMF of the cell, that is 1.50 volt, and the voltmeter reading, that is across the fixed resistor, which is 1.19 volt. So let's write it down here, 1.19 volt and 1.50 volt. Now we have to find the resistance of the LDR. As this is a series circuit, we have to understand that in series circuit, the current will stay the same and the voltage will divide. So the voltage across the LDR is simply 1.50 minus 1.19, which corresponds to 0.31 volt. Now, as you know, the voltage of the LDR, if you can recall the equation, V equals to IR, and subject R from there, you will simply get the resistance of the LDR. So in this case, we have to find the total current in the circuit. And as this is a series circuit, current through the fixed resistor and current through the LDR is going to be the same. So you simply find the current through the fixed resistor. And the formula is V is equals to IR. We're trying to find the current in the circuit. So I is equals to V by R. And the voltage across the fixed resistor is 1.19. And its resistance is 5 kilo ohms. That is 5,000. And the value of current is 2.38 into 10 to the power minus 4 amps. As you know the current, as you know the voltage across the LDR, it's simple to find the resistance, which is V is equals to IR, R is equals to V by I, and the voltage is 0.31 divided by 2.38 into 10 to the power minus 4, and the resistance would stand for 1302 ohms. And now we have to see the significant figures that we're talking about. So we have to go for 3 significant figures, and this is actually 4 significant figures. So you must round this up, and we're getting 1300 ohms. Now, in question D, the question is talking about that from this circuit, you really cannot find the resistance of an LDR as it changes due to the light intensity falling on it. And if you're talking, and the teacher is saying, when lights are on, the resistance of the LDR is 9 ohms. And the voltmeter resolution, what is the meaning of resolution? It is the smallest division possible by an instrument or an apparatus. So the voltmeter has the smallest division of 0.01 volt. And the teacher is saying, by using this circuit, you can never find the resistance or the voltage across the LDR. Now we have to figure out why is this so. So they have given you the smallest division of the voltmeter, that is 0.01 volt. So if we can find the voltage across the LDR when its resistance is 9 ohms, if we can find this and compare that value with this resolution of the voltmeter, we might get an answer. So let's see. First of all, we have to find the total current in the circuit. And we know the total resistance of the circuit is 5 kilo ohms, that is of the fixed resistor, plus 9 ohms, that is of the LDR. By using that, you can find the total current in the circuit. So again, V is equals to IR. I is equals to V over R, and V was 1.5 volts, and R is 5,000 plus 9, that is 5,000. So the current from here is 1.5 over 5,000 plus 9. So we're simply getting 2.995 or 2.99 into 10 to the power minus 4 ampere. That is the total current in the circuit when the resistance of the LDR is 9 ohms. By simplifying the voltage across the LDR, that is V is equals to I times R, 2.99 into 10 to the power minus 4 into 9, which is 2.99 into 10 to the power minus 4 into 9. And we get, which is 2.69 into 10 to the power minus 3 volt. So if you round this up, you can simply get 2.0027 volt. So if you further round this up, you can get 0.003 volt. So as the voltage across the LDR is 0.003 volt and the resolution is only 0.01 volt. So the value of LDR is actually smaller than the smallest division of the voltmeter. Hence, from this specific circuit, you cannot find the value of voltage. So as 0.003 volt is actually less than 0.01 volt. And it is because of this reason, as the voltage of the LDR is 0.003 volt, which is even smaller than the smallest division of the voltmeter, you cannot use this circuit to find the voltage of the LDR. This question is about the energy levels for an atom of hydrogen. We can see the energy levels. And this question is talking about the electron in the atom is absorbing an incoming electron and is also absorbing the incoming photon. So what happens in these two different scenarios? As you can see, we have 4 marks. The first 2 marks will be for the electron absorption, and the other 2 marks will be for the photon absorption. So we have to remember one thing. That whenever you're talking about an electron absorbing a photon, the energy of the photon must be equal to the energy level difference of the atom. If not, the electron will not be absorbing the photon. As we have always seen that whenever in this type of a question, we write one line, that is, one electron will absorb the energy of one photon. So this clearly means the electron absorbing the photon is discrete. It will absorb discrete number of photons. If you think about this in this way, that you are moving up a building and you are taking the stairs. As you're going up the stairs, you simply cannot be in between a second stair and the third stair. Either you have to be in second stair or either you have to be in third stair. There's nothing in between. Similarly, an electron in the ground state will be in minus 3.4 electron volt or in minus 1.5 electron volt or in minus 0.85 electron volt and nothing in between. If it goes to 0 electron volt, that is basically the ionization energy, which means the electron has emitted from the atom. That's a different case. In this case, as we are saying, that the electron needs to move from 13.6 electron volt to minus 1.5 electron volt. So the absorption spectrum is from here to here. And it needs an energy which is equivalent to, and it needs an energy that is equivalent to minus 13, minus 1.5 electron volt, minus 13.6 electron volt, and that is 12.1 electron volt. So the electron needs to absorb an energy of 12.1 electron volt. Now we have to understand the difference, the electron and the photon. So as you can see, the electron has an energy of 12.3 electron volt, and still the electron in the atom is absorbing the incoming electron and jumping to a higher energy level. But when the photon has the same energy, the electron in the atom is not absorbing that photon and not jumping to a higher energy level. So in case of an incoming electron, the energy does not need to be equal to the energy level difference of the atom. The energy can be higher as that additional amount of energy. And what is the additional amount of energy? The electron in the atom needs 12.1 electron volt, but the incoming electron has an energy of 12.3 electron volt. And there is an additional amount of energy of 0.2 electron volt, right? So this additional amount of energy, which is 0.2 electron volt, is actually the kinetic energy left for the incoming electron. Hence, in this scenario, in this question, and from this question, we can understand the electron in the atom can absorb an incoming electron whose energy is equal to or greater than the energy level difference of the atoms, but the electron in the atom will absorb a photon only if its energy is equal to the energy level difference of the atom. That is the difference over here. So if you want to write the answer, we can see. So this is the answer. The electron in the atom needs an energy of this, as we have previously discussed, that 12.1 electron volt to move from this energy level to this energy level. And the additional 0.2 electron volt is actually the kinetic energy left for the incoming electron. So we have written 2 marks for the incoming electron. Now we're going to write 2 marks for the photon and the energy level difference. So as we know, 1 electron in the atom will absorb the energy of 1 photon. So we are showing here the discrete thing that the electron will be absorbing the photon in a discrete way. And the energy level difference is 12.1 electron volt. But the energy of the photon is 12.3 electron volts. As the energy level difference and the energy of the photon are not matching, the electron in the atom will not absorb the photon, hence it will stay or remain at minus 13.6 electron volt, which is the ground state.